All right, class, welcome back. Thank you for your understanding for my last minute cancellation of Thursday's class. Um, so what I'm going to do in this lecture is we'll continue what we have discussed for Laplace transform or chapter 6 material. Um, so we have introduced the definitions, right? And I mentioned the focus will be the unilateral Laplace transform. We gave a few examples showing how to use the definition, the integral, to solve for the Laplace transform. And I mentioned here that there's a table 6.1 on page 372 that you can conveniently use a bunch of things that are pre-calculated for you. And of course, similar to Fourier transform, there are a number of properties that can be combined with those pre-calculated building block signals that can help you derive the Laplace transform of a number of other signals. To introduce a few of them already, um, and one thing is, well, we can do Laplace transform using the properties, and there's a need to do inverse Laplace transform, meaning give you this function of s, how to calculate the time domain signal f of t, right? So fortunately, in this course and also in systems and control, when we talk about inverse Laplace transform, we usually do that for a very specific type of functions. Usually is this division of two polynomials. And the typical method to use is the partial fraction expansion, where you can find in the background chapter from page 24, in combination with the building block signals, like the exponential signals, unit step signals, delta function, and so on. And last time we gave a couple of examples showing how this can be carried out, especially um, before we do anything, do the partial fraction expansion, you want to examine the order of the polynomials in the numerator and the denominator. Okay, we discussed two separate cases, and also when it comes to the root of the denominator, whether or not the roots are distinct or repeated. Like in this example, we have different methods, although they are quite similar to each other, to solve for the undetermined constants a, b, and c. All right, so today we're going to continue our discussion. So before going forward, let's look at another example just to wrap up the discussion above. So in the previous example, f of s is given as this polynomial s plus 1 over s plus 2 squared and s plus 3. Now, and we have solved the f of t, which is above. Now let's assume I multiplied this guy with e to the negative 4s, and I ask you to find f of t, the corresponding Laplace transform. So how do we go about this? Now, to solve this, we need to use one of the properties we discussed above, that is about the time delay. So if we move up a little bit, we will see this property and this property. So that said, if you have a Laplace transform being multiplied by an exponential term, e to the negative s times t naught, then you can temporarily ignore that exponential term and focusing on calculating the inverse Laplace transform of the previous preceding term f of s, just like what we have did in Tuesday's class. And then as soon as that's done, you apply the time shift properly to all the terms in that inverse Laplace transform. All right, so going back to this particular example, right? What we have here is we have this guy that we have calculated earlier, and then we have the second term, which represent a time delay. And the time delay here, the T naught is equal to 4 since e to the negative 4s, right? If you remove this e negative sign and s, whatever is left in this exponential term is the time delay. So if this is the case, then we can directly write down f of t, which will be the time delay version of the signal that I just underlined. So applying time delay, this is what we have learned in chapter 1. So minus 3, and you identify all t's. U of t minus 4 plus 2 e to the negative 2 t minus 4. So shifted by 4 time units, t minus 4 minus t minus 4 e to the negative 2 t minus 4 u of t minus 4. And that's it. Okay, so this is how we typically solve for inverse Laplace transform. So you may wonder, well, when do we actually need to do this inverse Laplace transform? And this is what we're going to talk about next, which will be, the scenarios that we can apply Laplace transform to help do certain calculations related to signals and systems. So let's go back to our previous discussion in chapter 2, right? So we have an LTI system, linear time invariant system. We have input f of t, we have output y of t. And let's assume I'm looking at the zero state response. So I know this is equal to f of t. My input signal convolution integral is my h of t. And let's narrow down our discussion under the following assumptions. Assumption number 1, we're looking at a causal system. The system is causal. System causal meaning that unit impulse response, h of t, is 0 for all t negative. Okay? Because the unit impulse response is the zero state response when the input is the delta function, which only appears at time t equal to 0. So if the system is causal, it shouldn't respond to it until after this delta applies. Secondly, let's assume the input signal is also causal. Meaning f of t is also 0 for all t negative. Because t equals 0 is kind of an artificial point, we choose to denote the starting point of our observation. So we can choose the input signal to be 0 before everything gets started. Now, in chapter 4, we have obtained the following. That the Fourier transform of the output is equal to the Fourier transform of the input signal times the frequency response function. And we know the frequency response function is the Fourier transform of my unit impulse response. Right? This is what we have discussed earlier. And of course, the unit impulse response, the frequency response function h can also be obtained through our transfer function. And also, I want to mention again that this is only for asymptotically stable system. So if you want to utilize this, it must be asymptotically stable system. Otherwise, none of the calculation will make sense. Now, what we can also find out using the same methodology is that the Laplace transform of my output signal is equal to the Laplace transform of the input signal times the Laplace transform of h of t. Okay? Using the same methodology as in chapter 4. That you apply the integral substitution of variables, separating the terms in the convolution integral, and so on. So the same method, I'm not going to prove this again. And since in Fourier transform, this is what we have obtained. We know the Fourier transform of h of t is the frequency response function. It is natural to guess whether or not the Laplace transform of h of t, unit impulse response, is equal to the transfer function h of s. This is the transfer function. And we know the transfer function can be calculated very easily through the differential equation. This is what we have done in chapter 2 again, and you have done it as the first exam. And if this is the case, right, we haven't shown this yet, but if this is the case, it indicates that h of t is equal to the inverse Laplace transform of h of s. And we have already discussed above on Tuesday how to calculate an inverse Laplace transform. And if this is true, solving h of t can be carried out in the different direction than what we have learned in chapter 2. Okay, so this is what we're going to do next, and we'll illustrate this using an example. So let's start this example. I'll move this up. So the example is like this. Let's consider an LTI system like what we have done in chapter 2, which is defined by a second order differential equation. And I'll make up the numbers such that the calculation will be simpler. 2y equal to 4 df dt plus f. Right, we have a second order differential equation. And what we're going to do is I'm going to apply Laplace transform on both sides of this differential equation because each of the term is a signal. So this is the second order derivative, right? So the left-hand side will be like this. We'll do it from the right to left. Do it for 2y first. If we take the Laplace transform of 2y, it will give me 2 times y of s. If I do the Laplace transform of 3 times dy dt, this is where we're going to use one of the properties that we discussed on Tuesday, that this is equal to 3 times s times y of s minus the initial condition of y. Y 0 minus. Of course, they'll be connected with the plus sign. And finally, for the first term, second order derivative term, if we take its Laplace transform, right, the result will be s squared y of s minus s times the initial condition and minus the initial condition of the first derivative. Let me use y dot to indicate it. So this is the Laplace transform of the three terms on the left-hand side of this differential equation. On the right-hand side, it's going to be similar. We'll be equal to 4 times s times f of s minus initial condition of f plus f of s. And now let's organize the terms. On the left-hand side, let's look at all the terms that have y of s involved. 1, 2, and 3. On the right-hand side, let's also look at all the terms that have f involved, 1 and 2. Now let's do the combination such that I'll group everyone with y of s first. That'll give me s squared plus 3s plus 2. Okay. And the rest of the terms, I'm going to move to the right-hand side. So that it means this, and this will be moved to the right-hand side. Okay. So on the right-hand side, let's also do something. Let's do f of s. And this will be multiplied by 4s plus 1. And since I mentioned above, we only discussed the case where the input signal is causal, meaning before t equals 0, there's no input signal involved. And if this is the case, this term will be 0. Right? There's no initial condition for the input signal f, it's 0. So the rest of the term will be plus, right, s plus 1 initial condition of y. So since we have this one and this one, and then plus the initial condition of the first derivative of y. And finally, let me do y of s. I'll divide this polynomial to the right-hand side of this equation. So 4s plus 1 over s squared plus 3s plus 2 times f of s and plus s plus 1 y initial condition plus y dot 0 minus over s squared plus 3s plus 2. Sorry. Let's go back to this again. Okay. So this is what we obtain. What does it mean? What does this indicate? Right? What message does this equation carry? This is something we want to figure out. Now, think about the following scenario. Oh, sorry, I need to correct something. This is should be s plus 3 instead of s plus 1. Since there's a 3 here, that'll be multiplied by that initial condition of 1. So what does this mean? This means that if both initial conditions y0 and y dot 0 are equal to 0, then this is the only term that will remain. And using our language from chapter 2, that means this is the zero state response. On the other hand, if the input signal f of t is 0, that means f of s is 0. And if f of s is 0, the only terms left on the right-hand side will be this guy. Which is the response of the system when the input is 0, or in our chapter 2 language, this is what we call the zero input response. And apparently what we have just done here is we introduced a new method to calculate the zero input response and zero state response of an LTI system through Laplace transform. And this equation carries a lot other messages, right? For the zero input response, for instance, as soon as you know the input, the initial condition, plug them in, take the inverse Laplace transform, you got the zero input response. For the zero state response, right? First of all, this guy is what? This is our transfer function. And what we have just conjectured above, right? The zero state response, y of s equal to f of s times the Laplace transform of h of t. And we sort of guessed the Laplace transform of h of t is equal to the transfer function. And this is confirmed here, that y of s is indeed equal to the transfer function multiplied by the Laplace transform of the input signal. So this tells me the transfer function h of s is indeed equal to the Laplace transform of h of t, not unit impulse response. And of course, solving h of t will be pretty simple. You don't have to follow a long procedure anymore. For instance, in this particular example, I only have to take the inverse Laplace transform of this 4s plus 1, s squared plus 3s plus 2. And we have done this in the previous examples for similar case. Right, you do a over s plus 1 plus b over s plus 2. And you solve for a and b using the cover-up method. And I'll directly give the answer with the calculation to you. After solving a and b, applying the inverse Laplace transform, we can find out h of t is minus 3 e to the negative t ut plus 7 e to the negative 2 t ut. And I encourage you to use the chapter 2 method and check whether the h of t is calculated correctly here. Okay. Now, if we go back to this equation, right, we have also this blue box. You can do the zero input response based on the initial condition. And let's do an example to check whether or not this is true. So let's assume, for the same example, that I know the initial condition, this is equal to 1, and the initial condition of the derivative is equal to 2, and I want to find the zero input response. Okay. So the zero input response is the inverse Laplace transform of, going back to the equation in the blue box, s plus 3 times the initial condition of y plus the initial condition of y dot. So since I have both of this information, s plus 3 times 1 plus 2 divided by and s plus 1, s plus 2. Right? Or s plus 5 on top, and then s plus 1, s plus 2. Solving this inverse Laplace transform, we can use the partial fraction expansion again. In solving A and B, right? So A will be minus 1 plus 5 over minus 1 plus 2, which equals 4. And B will be minus 2 plus 5, since B corresponds to s plus 2, over minus 2 plus 1, since you covered this s plus 2 term in the denominator. And this will be negative 3. So in this case, it means the zero input response under that initial condition is 4 e to the minus tut minus 3 e to the negative 2 tut. And again, you can check whether or not this is correct by using the chapter 2 method. And I strongly encourage you to do that and make sure um, you're able to do the calculations. And of course, as far as the exam is concerned, as I mentioned, I won't force you to use a particular method to solve zero input response, zero state response, unit impulse response, and so on. You can choose the one that fits your capability, your preference the best. If you feel like you want to use the Laplace transform to solve the zero input response, that's completely fine with me. If you feel like you want to solve the zero input response using the chapter 2 method, to me, which is more straightforward, you can do that as well. Okay? So there's no forcing of use a particular method. Now, what else can we do? Now, we can also use this method to calculate the response, right? So now let's assume for the same system, right? I have f of t equal to e to the negative 3 tut. I want to know the zero state response. How to calculate this? Right? So y of t is representing the zero state response. And if we use the Laplace transform y of s to represent this Laplace transform, from what we know above, it should be equal to the Laplace transform, the transfer function of the system, multiplied by the Laplace transform of f of t. Laplace transform of f of t. And in this case, it will be 4s plus 1 over s plus 1, s plus 2, times 1 over s plus 3, which is the last term. So using partial fraction expansion again, so we know y of s should be, in this case, with 3 terms, a over s plus 1, b over s plus 2, and c over s plus 3. In solving a, b, and c, we can use the cover-up method again. So to solve for a, it corresponds to s plus 1 equal to 0, or s equal to negative 1. So I replace s with negative 1 and cover up the s plus 1 term in the denominator. So I only have s plus 2, and s plus 3, where s is equal to negative 1. Right, and do the calculation. I have minus 3 on top, and I have positive 2 underneath. B will be similar, 4 times negative 2 plus 1 over s plus 1, s plus 3. In this case, doing the calculation, we have b equal to 7. Since it's negative 7 on top and negative 7 in the denominator. And finally, c will be equal to 4 minus 3, since it corresponds to s plus 3 plus 1. So in the numerator, I have what? I have minus 11, and I have s plus 1, s plus 2, where s is equal to negative 3. And again, organize the terms. I have minus 11 on top and positive 2 in the denominator. So that means I can directly write down y of t now. When you get more proficient with this process, as soon as you have obtained all the constants, you apply the inverse Laplace transform of the building block signals, the exponential signals in this case, and you can get the zero state response immediately. Minus 11 over 2 e to the negative 3t ut. And there you have the zero input response. In chapter 2, we can also do this. In chapter 2, we solve zero state response using convolution. And most of us do that through the convolution table in the textbook. And through your homework and the exam questions, you know using the convolution table and doing the calculations are not that convenient. Now, through the Laplace transform, it basically, at least from my perspective, provides a more convenient, easy to carry out method, computation method, to derive the zero state response. So up to this point, we have discussed a number of different scenarios where you were given the linear time invariant system. You have an input and you're trying to find an output. This is one of the problems that we discussed at the beginning of this class that we're trying to learn how to solve in this particular class, right? Given the system characteristic, given the input signal, how to find the output. Now, we have covered, I think, all the cases we have discussed, and basically all the methods we have discussed. So here I would like to give kind of a summary version, give you a high-level overview or review of what we have discussed through a diagram. And hopefully this diagram can be used for you to understand and connect different dots in this class that we have learned in this class. All right, so this diagram will look like this. We'll have kind of three parts. One is my input. Second, on the right-hand side, I'm going to draw the output signal. In the middle will be my system. All right, of course, for the system we discussed throughout this semester, we focus on linear time invariant systems. So make sure, again, you understand what does linear mean, what does time invariant mean, and how to utilize them. For linear time invariant system, the very basic way to represent it is through a differential equation. Right, this is what we did in chapter 2. There are other ways to represent a linear time invariant system we have discussed in this class. One of them is the unit impulse response. H of t. The next is the transfer function. H of s. And the last one we discussed in this class is the frequency response function. Notation-wise, it can be h of omega, and sometimes the book also use h of j omega. If the notion comes from chapter 2, where we utilize the frequency response function, but in terms of h of j omega, meaning it's the transfer function with s replaced by j omega, and both referring to the same thing. And one particular thing to mention is if you want to use the frequency response function, you have to make sure the system is asymptotically stable. If the system is not asymptotically stable, you cannot use frequency response function in any calculations. All right, so this is the system block in this diagram. Now, in terms of signal and response, there are different classes that we have discussed in class. First case is when you have a causal signal, usually in the form of e to the at times u of t. And the way to solve the response in this case is we'll focus on the zero state response. And two methods we have discussed. First is whether or not you use the convolution integral, like what we did in chapter 2, or like what we did in chapter 6, you multiply transfer function with the inverse Laplace, the Laplace transform of the input signal, and eventually solve for the inverse Laplace transform. Okay? And the mathematical tool involved in the middle, including partial fraction expansion. Second type of input is when you have a constant, f of t equal to a constant c. This is our DC input. And when we talk about the response, in this case is typically referring to the force response. It's C, the amplitude of your DC input times the DC gain of the system. And if you ever wants to use this, in the following two other scenarios, you are looking at asymptotically stable systems. And we're going to group all of them together. So next, if you want to do f of t equal to an exponential, everlasting exponential signal, from what we did in chapter 2, we know the response will be h of s equal to lambda times e to the lambda t. And finally, for f of t equal to a cosine omega 1 t equals theta, a sinusoidal input, the response will be a times h of j omega 1, absolute value times same cosine, same frequency, and with the phase modified by the frequency response function evaluated at that frequency. And as you can see, for the last case, you're using asymptotic stable system because you're using the frequency response function. So this has to be guaranteed. For the force response, same thing. If you want to do it, you're basically assuming the frequency is equal to 0. So that one has to apply as well. All right, and for the middle case, where you have an everlasting exponential signal, although it's not usually explicitly required, but also in most cases, if you ever want to do a calculation like this, we're going to require the system to be asymptotically stable to carry out the calculation. Now, apart from the cases that is covered by this spectrum, the input and output relationship, there's one more case that we discussed in chapter 4 and 5. That is the ideal low-pass filter. That has these two corner frequencies. It can filter out the frequency component from the input signal that is above the corner frequency or the cutoff frequency of the filter. All right. So through this diagram, we can basically have an overview, of 30,000 feet overview of what this course has covered. Right? Differential equations, the basic representation of a linear time invariant system is usually derived based on the mathematical model or the electrical system model, mechanical system model. And then from there, I can convert a differential equation into a unit impulse response, a transfer function, a frequency response function using the method we have discussed. Convert one into the other representation. And for the two transforms, as I mentioned, Fourier transform, its advantage is in the fact that this omega, or omega in this j omega, has a physical meaning. It actually represents this frequency component in the signal. But it has a lot of restrictions as well, as we discussed. For the Laplace transform, which in this case will have the transfer function is in the Laplace transform, its advantage is the convenience in calculation, especially in calculating the response of an LTI system. Right? So next, we'll focus on the Laplace transform, and especially how we can utilize the transfer function and the Laplace transform tool to help us better understand and analyze LTI systems. Right? So we'll start from some simple examples. When the transfer function is in the form of the division of two polynomials, it's kind of simple way I've discussed it earlier through a few examples. But there are some special scenarios that are also worth mentioning. For instance, sometimes you want an LTI system to represent a time delay. If you want an LTS system to represent the time delay, that means h of t is equal to delta of t minus t naught, right? So when enter delta t into the system at the input, the response is t minus delta of t minus delta t. It appears at t equal to t naught. So with the time delay, with the amount of t naught. So the corresponding transfer function is going to be the Laplace transform of h of t, as we mentioned. And through the discussion we have above, since it's a time delay, we take the form of this exponential function, right? So this is a simple example. Now, other things that are worth mentioning, for instance, we can have a integrator. Integrator means the output y of t is equal to the integration of my input. Of course, we only look at the signal, the input signal, which is causal, right? So we don't have to worry about the input signal before t equal to 0. So this is why I have the lower bound equal to 0 minus. How to find the transfer function in this case? So the response, the impulse response in this case is going to be equal to u of t. This is something we discussed earlier. And this is something that you also have looked at in one of your homework questions in chapter 2. Now, the transfer function, which is the differential, the Laplace transform of h of t, will be equal to 1 over s. And of course, in this case, for this particular case, you can also rewrite it as dy dt equal to f. And you can find out kind of the same as well, have the same answer as well. So this is a couple of examples. So in system theory, sometimes we have these smaller building block signals. And sometimes we want to connect multiple systems together to form a more comprehensive functionality. Let's see how that can be done. The simplest way to connect two systems is through a serial connection. So the output of the first system becomes the input of the second system. Right? So like when you play electrical equipment, right? The output from your electrical musical instrument will be connected to the amplifier. So the output of the instrument becomes the input up to the amplifier. And the output of the amplifier will be entered into the loudspeakers. So the output becomes an input of the next system again. And if, let's say, we have f of t as the overall input and y of t as the overall output, and if suppose we know the impulse response of the subsystems, meaning we also know the transfer functions, how do we find out the overall output? Right? The output is pretty simple. Y of t should be equal to h2t, the second system's impulse response, convolution integral with its input. And the input here should be h1t convolution integral with f of t. And of course, we can write it, since it doesn't matter which one comes first, which one comes second. We can do it all the way from the beginning. And the star represent convolution integral as usual. Now, if we do this through Laplace transform, y of s will be h2 of s, the transfer function of the second system, times the Laplace transform of its input, which will be h1 of s times f of s, the output of the first system. Or again, we can write it as in the order that we feel comfortable with. For instance, we can do h1s, h2s times f of s. Or that means we can view the two subsystems as a whole and say this overall system has a transfer function hs equal to h1s times h2 of s. Or we can say its unit impulse response ht equal to h1t convolution integral with h2t. It doesn't matter which way we go. We can combine the terms such that the product of the transfer function or the convolution integral of the two unit impulse responses will represent the overall combined effect of the two subsystems. And of course, as we have seen throughout this chapter, the advantage brought by the Laplace transform is to convert a calculus, meaning differentiation or integration calculations, into algebraic calculations like multiplication, partial fraction expansion that's just plus, minus, and multiplication. That's pretty simple. So through the Laplace transform, the calculation can be the complexity of the calculation can be greatly reduced. And for this, we can look at just one simple example, and this is something that we have seen before, right? Let's say we have a transfer function h of s equal to, I'll just kind of randomly give some numbers. Right, if we have this transfer function connected through this product, it corresponds to the serial connection naturally. And it can be viewed as we have the first subsystem being this conventional transfer function, and it's being serially connected with the second part, which represent the time delay as we have discussed. Okay. The second commonly used structure where multiple linear time invariant systems are connected is through parallel connection. Where two subsystems share the same input. And then the overall output is the summation of the two. So using the same idea, we know that since the summation of the outputs of the two subsystems, it should be f of t convolution integral with h1t, that's the output of the first subsystem, and f of t convolution integral with h2 of t, that's the output of the second subsystem. Or by combining the two terms, this is what we eventually obtain. And in terms of the Laplace transform, it's pretty easy that we can obtain a similar form. That if we want to view the overall parallel connected system as a whole, the overall transfer function will be the sum of the two individual sub-transfer functions for the parallel connection. And the overall impulse response would be the summation of the two individual impulse responses. So this is for parallel system. And in both cases, because the connection is rather simple, using either the impulse response in the time domain ht's or the transfer function h of s's do not make too much difference in terms of the appearance of the formation. Sometimes we have slightly more complicated scenarios that are also commonly used in practice, especially in what is called a control system. I'll first give the diagram of that system, the structure's connection, and I'll explain each of the blocks. So the input is usually denoted as R of t. It's slightly different than what we have. It's going to be the difference between two signals. The resulting signal is called E of t. It's being connected to a block with transfer function g of s. And the result is the output is connected to or entered to a system with transfer function p of s. And then the output, on one hand, is being observed by the external users or whatever. And on the other hand, it will be sent to another block, let's call it h of s. So of course, for h of s, the input is on the right-hand side instead of the left-hand side. But if you follow the direction of the arrows, it's easy to track where does the input comes from and where does the output go. So we're looking at this system. Of course, instead of having 2 blocks, we have 3 blocks. All right. So for this system, it's usually easy to look at things in the frequency domain, meaning in terms of their Laplace transform. And what is the system usually used for? It's usually used, as I mentioned, a control system. The control system will be, you have a reference input, R of t. It can be, for instance, you turn on the air conditioning in your home. You set the degree to be, let's say, 72 degrees. And then what's going to happen is the thermostat is going to measure the actual temperature in the room, y of t, through a certain sensing mechanism. So h of s represents that sensing mechanism because, for sensors, it takes time, for instance, to actually measure the temperature change. So it's not going to be static or instantaneous. Okay? Try to think about what a static system means. It means everything is instantaneous. Now the sensor will report a measured temperature compared with your reference. For instance, the current room temperature is 60 degrees. Your set point is 72. There's a 12-degree difference. That difference is our E of t, and it's called the error signal. The error signal will be entered into a controller. Which calculates and actuates the control actions. For instance, how fast you want to blow cold air out, right? or how much power you want to apply to the heating coil. Then the controller and the actuator sometimes implement the control actions will blow the air into the room, and the system you're controlling is called the plant. In this case, will be the room temperature, will be the room air. Represent the dynamics characteristics represented by this P of S transfer function. And of course, out of the plant, you care about the room temperature if you're dealing with air conditioning, Y of T. And this completes this, what we call the closed loop system, right? So this is Y of T. Right here, we also have Y of T and Y of S. Now, if we only focus on the Laplace transform at the output of the sensor, you have what? H of S times Y of S. And this mechanism is what we call a feedback system. You implement a control action, you observe the output and feed it back to be compared with the reference to drive the future control actions. How do we analyze the system? How do we find out eventually the relationship between my input, the reference, and the output signal? Well, it's not very difficult. We have already done this part of it. If we only focus on the forward loop, meaning starting from the input to G of S to the output of P of S, it's easy to find out that Y of S, the output, is equal to G of S times P of S. These two blocks are connected in the serial manner multiplied by E of S, and the arrow signal being the input to the controller. And E of S is the difference between the reference and the measured output. And plugging E of S into the equation on the left. So we're going to do, we take this term, I'm going to plug that into this E of S. Right? That means Y of S will be G of S, P of S times R of S minus H times Y. Reorganizing the terms, I put everyone with Y of S on the left hand side, so Y of S already, and you have this one with Y of S. I'm going to move that to the left hand side, but before that you have to multiply that with the G of S and P of S in front of it. The negative sign will become a positive sign when I move that to the left. This is equal to G of S, P of S times R of S. Now, all terms on the left has Y of S involved, and the only term on the right you have R of S. These are the Laplace transforms of the input and the output signals. So one step later, we'll have Y of S equal to G of S, P of S divided by 1 plus G of S, P of S, H of S. Times R of S. And this is the transfer function of the above closed loop feedback system. Right? Meaning if we wanted to know the transfer function of this whole thing from the reference to the output, this equation is the one to use. Then you can say air conditioning, right, temperature regulation. You can say cruise control on your car, This will be the speed regulation. And there can be multiple things where, for instance, on a Segway, you're maintaining a pose such that you can remain at the upright position.